Students, let us now study moving coil galvanometer. So basically a galvanometer is a device to detect the current in conductor. Okay, whether there is a flowing current or not is detected by a device which is called galvanometer. Okay, so there are two or more types of galvanometer, like moving coil galvanometer and suspended coil galvanometer. Okay, suspended coil galvanometer you will study in college, but moving coil galvanometer we study in class 12. So in this lecture I am going to teach you the principle and the construction. Okay, so first of all, before going into these many things, I will tell you the some diagram of this galvanometer. So we have a two bar magnets, north pole and south pole, which is curved one. Okay, so these two magnets are curved magnets like this. Okay, like this and like this. So in between this magnet we place a cylindrical core like this. Okay, so this is my cylindrical core and it is like this. Okay, I have got one magnet here, I have got another magnet here like this. Okay, and between them I have a cylinder like this. And in real life the galvanometer is just like this. So this is my galvanometer. This is how it looks like. Okay, so there are pointers, there are magnets. So here if you see inside there will be a magnet. Okay, okay, so I will not open it. Now in this this cylinder I will have a wire on it. Okay, I will wind a wire all over it like this. Okay, now in some galvanometer you can also have, you will have some frame here. Okay, you will have a frame. What kind of frame? Rectangular frame, and in that rectangular frame the wires will be winded. Okay, for an example, yes, there is one. So if you have like this, okay, if you have, it is just like this rectangular frame. What? Rectangular frame like this, and on this I will wind a wire. Then the winding of wire will look like a rectangle, isn't it? So this is how it look like. So this is the cylinder. So this is my cylinder and these are my rectangular wires where I have done in this form. Okay, so red lines represent rectangular thing, and this is my spring. Okay, so spring has got some important function which we'll discuss in its working parts. Okay, so here I have denoted this spring in this form. Okay, and this spring and the coil and this cylinder is connected. Okay, and also remember there is a pointer attached with this cylinder like this. Okay, like this. So now whenever it rotates, whenever the cylinder rotates, this pointer will also rotate in this form, and you will get the some marking, some measurement over here. So you will have something like this. So this is my pointer. Okay, now say let me go to the, and this is my scale for measurement. First of all, the principle. Now once the diagram is done, the principle is that it works on the principle that whenever a rectangular loop is placed in a uniform magnetic field, it will experience a torque. Okay, so this is my torque. Tau is equal to, we know that in the last lecture we have studied National Basketball Association of India. Okay, sine theta. So I will write N I B, not B, A B sine of theta. So you can remember National Basketball Association of India sine theta. So this is the principle. Now again I will repeat, you have to write, it works on the principle that whenever a rectangular loop Okay, whenever a rectangular current carrying loop is placed in a uniform magnetic field, it will experience a torque. Okay, and that torque is this one that we have derived in the last lecture. So this is my sine theta. Now if you look at here, okay, this is very important concept. This is the magnetic field going from north pole and entering into the south pole, that we know. But if you see here, this is going like this. Okay, this magnetic field is going here and reaching here, isn't it? Now whenever you see this magnetic field, it is something like this, isn't it? But what do you think is that it seems like that it is intersecting and crossing, isn't it? It is going and entering here and it is coming here, and these two magnetic field lines are intersecting. It means that it is violating the properties of magnetic field. That magnetic field will never intersect with each other. Okay, so in fact, how does it look like? Then it look like this. Okay, magnetic field is in this manner. So this dotted line is not important, but also I am telling you how it look like. Okay, so this is the magnetic field and this is the magnetic field. Now they are not intersecting with each other. This is how magnetic field is passing. Okay, so now next is my radial magnetic field. So why it is very important that the magnetic field in this galvanometer should be radial. Not only moving coil galvanometer, also in suspended coil galvanometer, the magnetic field should always be radial. Okay, radial means, so why it should be radial? It should be radial to give uniform magnetic field, to give very important. Okay, it was asked this time also, uniform in 2020 examination, uniform magnetic field and hence uniform torque. Now why uniform? Now if you see here, okay, I will make a small one. If you have, I will make it like this. Okay, so this is my half of the cylinder, and if you have this one, okay, so this is my north pole. Now it is not curved one, then what will happen? Magnetic field will go this side and magnetic field will go this side and magnetic field will go and magnetic field is going, magnetic field is going. Now tell me, not this, okay, it has to be something like this. Okay, so if you see here, now this is short, this is very short and this is very long. Okay, now one magnetic field is short and another magnetic field is long. It means that the magnetic field is not same, isn't it? Because magnetic field is a vector quantity. Now if you have this vector A vector and if you have this as B vector, then which is large? A vector is greater than B vector. So here then this wire which is here like this, okay, all the wire here will not have a uniform magnetic field because this is long, magnetic field is large, this is short, this is small, so this will also large. Okay, so then what will happen? There is no uniform magnetic field, isn't it? So we want the magnetic field to be uniform. Understood? So to have the uniform magnetic field, I have to have radial magnetic field by using a curved bar magnet. Okay, so why? To give uniform magnetic field and to give uniform torque. This is very important concept, like this. Okay, you can draw this one also if you want. Now let me go to the, okay, there is a frame on which I have to write there there is a frame on which the wire, this frame is rectangular frame. What kind of frame? Rectangular. Okay, rectangular. rectangular frame is there on which we wind the wire in the shape of rectangles. Okay, like this. Now next is cylindrical core, and there is a cylindrical core on which we place that rectangular frame. Okay. Now next is copper wire. So this copper wire is insulated. Please remember, insulated. It means that if they are like this, okay, even like this, then this current in this wire will not flow through this wire. It means that they are separate. Okay, so these are insulated copper wires which is used to wind all over the frame, rectangular frame. And next, what is there? There is a core bar magnet. Okay, so there is a core bar magnet to give radial magnetic field. Core bar magnet to give radial magnetic field. So all these are construction. Okay, so now there is hair spring. So this is my hair spring. Okay, why it is hair spring? Because this spring is very, very small, very, very thin. So it is like a hair. So this is called hair spring. So hair spring gives what does it gives? It gives what do you call this one? It gives in simple way, okay, external torque, external, external torque. Okay, so there is one more term for this which I will define in the next lecture. Okay, or you can also write to give external and restoring, restoring torque. To give external torque or to give restoring torque. What do you mean by restoring torque? Is that there is a wire, okay, there is a wire. Now if the current flows in this wire, then what will happen? It will experience, this is in rectangular form, it will experience a torque and it will rotate like this. If it is rotating in this direction, clockwise direction, then what will happen? This spring will try to restore this one. Okay, so it was just like this. It was at zero. Whenever the current in this wire like this flown, then it will rotate like this. Say for an example, it rotate like this, but it will remain here because of current and magnetic field and the torque. But because of this spring, what they do is they try to restore this to back. Okay, it was just like this. Current came, rotate, and because of that spring, it will try to restore its position. Restore. So that is why this is also called as restoring spring. Okay, restoring torque. Now there is a pointer. Pointer is connected on the surface of the cylinder. Where? On the surface of the cylinder. Okay, cylinder, which will give the reading on the scale. Okay, and there is lastly there is a scale which is used to see the angular deflection of the pointer of the meter. It means that if it is 0, then it may go like this 10 degree, 20 degree. Okay, so these are in degrees. Okay, 0 degree, 10 degree, 20 degree to see the angular deflection of the pointer. So these are the principle and construction of moving coil galvanometer. Thank you.